All right, so the first thing we have to do to, of course, benefit from this symbolic Python module is we have to do an import, and we import. One of the ways of importing it, I think we're just going to import it like this. Okay, like that. So we do an import of the module, symbolic Python as symbolic like SYM, like this. Then of course you can see the contents of the module, what's on offer. Like I explained last week, there is a whole lot which this module offers. There is a lot of mathematical functions and tools which the module offers. So that's how you do your import, and you see what kind of some of the things which are there. We at the moment, since people are just in third year, we just concern ourselves with some of the things which concern us. Okay. And basically, it's also an opportunity for you to look out for other things. What else could you use this thing for? You have, as a physics student, you've got a lot of mathematics which has to be done. So this module is actually very, very handy, and we'll try to show some of the things which it can do. Last week we did certain things, for example, some expansions, expanding, simplifying, and stuff like that, creating expressions. This week we'll try to add on what kind of things we can do, for example. So how do we do that? The first thing we're going to do is we're going to create some variables, some symbolic variables x, y, and z, using the symbols function here. Symbols function, so we give it a string of characters we want to use as variables in this case, so x, y, and z in strings like this, and this is going to create these symbolic variables like that. So when you run that, so that's what you get. If you check what kind of things you've created with x, it tells you that x is now a mathematical symbol, and also the same thing applies with y. Y is now a mathematical symbol. Then the same thing also applies with z, that is now a mathematical symbol. The first thing we want to do is, how do you create a fraction? Now, if you want to create fractions using numbers, you have to import this function from Sympy, symbolic Python. You have to import a function called rationale. So from Sympy, symbolic Python, import rationale. So when you run this, that's what you get. Now, once you have rationale here, with this function, you're going to give it what number is going to be the numerator first, and what number is going to be the denominator second. So when you do that, like this, like in this case, where 2 is going to be the numerator and 3 is going to be the denominator of this fraction, this is what you get. So you get a fraction 2 over 3. The same thing you can do with, if you want to create a fraction half. So in this case, you have what we have here, 1 is going to be the numerator, then 2 is going to be the denominator. You can do that. Then you can even go further. For example, you can add these fractions. You can even do addition of these fractions. For example, we have the first fraction which has got 2 and 3 as a numerator. Then you've got the second fraction which was 1.5. So we can add these 2/3 plus half. You can do an addition like that. When you add them as fractions, this is what you get. You get 7/6 as an kind of like, yeah, 7/6 like this. You can also do subtraction. It's possible for you to do subtraction. You can do subtraction like that. You get, when you subtract 2 over 3 minus half, that's what you get. And I think it's also possible for you to do you can do multiplication of the fractions. You get this, when you multiply them, you get 1 over 6. I am definitely sure it's possible also for you to do division. You can divide one fraction with the other, then you get that. So basically, once you create a fraction, you can use this fraction I've created to do all the fraction stuff, whether it's adding fractions, whether it's subtracting fractions, whether it's multiplying fractions, or whether it's dividing fractions. You can do that. Are we clear?
Yes, we are clear, sir.
Yeah, I think it's also possible to do another thing. Let's see. For example, you can raise this fraction to a power. Let's say to the power 2. When you do that, what do you get? Yeah, you can raise it to a power 2, this whole fraction. So 2/3 to the power 2, that's going to be 4/9. So you can do that. So all the basic mathematical things which after you create a fraction, the two fractions you've created, you can add them, you can subtract them, you can do all sorts of things. Yeah. It should also be possible, I think, to let me see. Fraction. Then you say rationale. Two-thirds. Then you can store a fraction which you've created. You can do that. Yeah. So you can store these things. These fractions you've created. These expressions. You can store them in a variable. Like in this case, I've given the name of the variable in which I'm storing it as fraction, for fraction. So once you store something in a variable like that, you can do all the good stuff which we have learned about when it comes to variables. Apart from doing fractions, there are also other mathematical functions and numbers which you come across in physics. For example, you've got constants, mathematical constants like pi. So here you could import pi. Remember, we imported symbolic Python as sim. Then you can do this pi, Sympy, then store it like that. Or you could say, either you do it like that, or you could say from Sympy, import pi. You do that, then you can display pi. There's your pi value. Or you could also say here, sort of doing this, you could say from symbolic Python, Sympy, import e. Now this e is Euler's number. You can say import e as e. Then you display e, that's what you get. Then also, in this case, here, this is the I for the complex number. So you can say from Sympy, import I as that. When you do that, that's what you get. Then also there is a number, for example, the infinity number. So you can say from Sympy, import. Now in the case of infinity, this is supposed to stand for infinity. These two O's, these are two small letter O's. So I press O and not that O and O, two small letter O's as infinity like that. I want to import it as infinity, then I press infinity and that's what I get. So those are some of the constants which are available for you to use. You've got pi, you've got e, you've got I, the complex number I, then you have this infinity. This complex number I, if you want to see if it's a complex number I, you could simply say I dot evaluate that, then you get you this, it gives you this. So that's your I. There. Okay. Do you have any questions on how we import pi, how we import Euler's number E, how we import the complex number I, how we import infinity from symbolic Python? Are we clear? Wape?
Yes, it's clear.
Okay.
But what is for a question?
Yes, go ahead.
What if at the same time we, like, on the same notebook, we are to import numpy? Does it mean when we call pi, we show the symbol, or maybe to show the value for pi, or maybe to just follow the order, the one you called last, it's one should be like.
Just a minute. Hello? 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 Okay, so if you are planning on using NumPy in symbolic Python, then in that particular case, you have to use aliases. For example, in the case of NumPy, you would have to say import. So we'll start with import NumPy as np. So I'll do this. Then if I want to access pi now using the NumPy way, with NumPy I'll say np.py. That's what I would get. So to differentiate, this is a pi I get from NumPy. The other pi with just pi, that's the one I got from symbolic Python. But if I want to be, if I just say pi, then there's going to be confusion. Probably the computer will get confused or something like that, or it will overwrite, or it will use the most recent one. Are we clear? Or I could also do the I could do the following. I could just say, remember, I could just say just do this sim.py. That gives me the pi. So I think the most efficient way in that case would be to go along this way, where I use this and I use this. Does that answer your question?
Yes, it does.
Okay. Of course, if you're using this way, if you do this, then you want the actual value of pi to use it in the calculation. Then you have to do this. Sympy dot evaluate f. If you do that, then it gives you the actual value of pi, which is almost the same as what you have here. So if you don't want it using a symbol, you want the actual value, then you have to use, at the end there, you have to evaluate what that particular symbol is, what actual value it's equals to.
Now, what if we add them, as in we add the Sympy plus the np_pi? What we get?
We can try. np.py plus Sympy. There. That's what you get. If you want the actual values, you want this pi to be evaluated, then you have to put evaluate at the end here. Evaluate function, like that. But if you just add them, this is what you get.
Yeah, that's the part I really wanted to see, as not to evaluate the symbol part.
Okay.
Just done it.
All right, that's good. Next, let's move on to some other functions. For example, there are some elementary functions like square root, log, and exponent, which also come with Sympy. So if you can import these, you can say from Sympy, import square root, log, and exponent. If we do that, then you can, after you do that, you can find the square root of 25, that's 5. Find the square root of log 100, it just gives you log 100, but that's not really what you want. Probably what you want is to evaluate what the square root is. So you put to evaluate, then it gives you this. For example, also the exponent of 2 is that 2 to the e to the power 2, but if you actually want what the value is, So you have to evaluate it. You'd say exponent 2, then dot evaluate, then that's what you'd get. So there are some functions which actually, when you run them, for example, the square root of 5 gives you something which makes sense. This other one, when you run it, it just gives you something which looks similar. So it means that you have to evaluate it so that you can get what the actual answer is, like that. So these are not the only elementary functions. We're just getting started with this bit. So I think the notebook is going to be improved later on, probably for use for next year. But for now, you can explore what's there in symbolic Python, and basically just trying to show you how certain things would work if you did that. You can also import trigonometric functions from Sympy, for example, sine, cosine, tan, cot, sec, cosec, and sin functions. These ones here, so import them. Then with sine, you can find the sine of 0 is 0, the sine of pi is 0, the sine of pi divided by 2, that's 1, the sine of 2 pi 3 is that, the cos of 0 is that, the pi of cos of pi is -1, cosine of pi over 2, that's of course 0. Then this bit here, you have that. So it also evaluates trigonometric functions. Tan pi 0 to that, pi to the power divided by 2 is infinity, pi divided by 4 is 1, and a bunch of other things. There's a function called sinc here. Also, it's a kind of a trigonometric function. Then of course there is the cotangent here. You can work out the cotangent. Then there's also sec. Then also the cosec, like that. So it works out like that. In the case of the sinc function, this is basically how sinc is defined. The sine of x divided by x. So the sine of x divided by x, it's anything else. It's sinc of x is sine x over x when x is not equal to 0, but when x is equal to 0, it's just equals to 1. So the sinc of 0, x equals to 0 is 1. Anything else like that, or infinity, you get 0. So basically, yeah, you have access to all the normal trigonometric functions, the ones you use. So they are there, you can access them, you can evaluate them, and you can use them. Any questions on the trig function, on the trigonometric functions?
No question.
Okay. Apart from just the trigonometric functions, you also have access to their inverses. Inverse trigonometric functions. Arcsine, arccos, arctan, arccot, stuff like that. For example, when we import them from symbolic Python, import arcsine, arccos, arctan, arccot, like that. Then for 1, the arcsine of 1, that's pi over 2. Arcsine of -1, that's minus that. 0, arcsine of 0 is that, get a 0. Then infinity, get minus that bit. Same there. Cosine of 1 is 0. -1 is pi. Cosine of 0 is pi, that, infinity, you get that, tan, like that. So basically you also get access to these inverse trigonometric functions. So when you look at this somewhere here, somewhere you will find a bunch of trigonometric stuff. Somewhere you find them there. Okay. Next, we also, apart from trigonometric functions and their inverses, you also have a family of functions called hyperbolic functions. Those are also there. The hyperbolic sine, hyperbolic cosine, hyperbolic cotan, or tangent, like that. So these you can evaluate. Like in this case, the hyperbolic sine of 1, it gives you that, but if you evaluate it, it gives you that, like something like that. So you can find out what hyperbolic functions are. Same with the hyperbolic cosine. If you do an evaluation of that, you get that. Then that's, you get this, that. Okay. Now, you might recall that sine and cosine functions are defined in terms of exponentials, e to the power something minus ix plus e to the power minus negative ix. And like that. Do you recall that? Divided by 2 or plus or minus?
I still recall, but not very much. Like,
yes.
The data series somewhere there.
Yes. I think it's I think for cosine cos x is equals to e to the power x plus, I think, e to the power e to the power ix, I the complex number, x then plus e to the power, I think, minus ix divided by 2. Then for the sine, I think it's e to the power ix, I think there's a minus e to the power minus ix, then divided by 2i, somewhere there. Now when it comes to the hyperbolics, the I is not there. Okay, so you can check out, basically you can just do a Google search of hyperbolic functions, then they're going to come out. Then you see how the hyperbolic cosine and hyperbolic sines are worked out. So basically this is how you do the evaluation. There are also inverse hyperbolic functions. For example, for the sine one, so you would arc hyperbolic sine, then arc hyperbolic cosine, and that like that. So in this case, these are the ones. These are what we got for the one hyperbolic sine, hyperbolic cosine, hyperbolic stuff like that. So if you do this arc hyperbolic sine of this number, this should give you back. Oh, sorry, I need to do an import. It gives you back your 0.999, which is just 1. That's what we have, what we had here. This number here, that's the number I put there. So that's what you had there. Then the other bits, if you also do the arc hyperbolic cosine of this number here, this is just the hyperbolic cosine of 1. That, if you do run that, you get that, and also this other one is just for the tangent, you get that. So basically, when it comes to these trigonometric and hyperbolic functions, they're kind of like catered for in symbolic Python. Of interest to us is a bit of calculus. When basically calculus is you doing limits, you doing differentiation, and you're doing integration. So what I'm going to show you in whatever time we have left is how do you do differentiation, how do you do integration, and of course there is some other thing which is at the end, how you do expansion, stellar expansion. So here we create an expression, x to the power 2 multiplied by y. So this expression we've created. So with this expression, we want to differentiate this expression. So you can write it like this. Expression, then you differentiate. Now this is for differentiate. This is a function differentiating. Then you're differentiating with respect to x. So if you do that, so if you differentiate this with respect to x, it's going to be 2xy. So you do that, you get your 2xy. If you differentiate it with respect to y, you get your, if you differentiate this with respect to y, you just get your x squared. Like that. Is that clear?
Yes, sir.
Okay, I think it's also, you should also. You have a question?
I joined the lecture, so kind of left behind on the part of x and y. Are those part of the defined functions for symbolic functions, or maybe
symbolic variables? The x and y, we have defined them upstairs. Yeah.
Oh, all right.
We have defined them when we're just starting here. So these are the symbolic variables x, y, and that's how you create them. So you have to define some variables which you're going to use. If you're going to use some variables, then you define them, and of course that's what we did. Okay, so basically it's
Right,
like,
okay.
yeah, it's like you doing your normal differentiation with pen and paper. Let me see, there's something else I want to try and find out if it can work from Sympy. Import diff. Yeah, so you can also, I think you can just import this function, differentiate. So because we use it like this, so you can also, I think it's possible to do this. Then if you import it like that, then you can say differentiate, then you put in expression there, the expression, then the variable with which you want to differentiate with. So in this case, I want to differentiate with respect to x. I get that. So the same expression, what you have done up here. So there are two ways of doing it. Either you do it like this, expression dot differentiate, or you can just import your differentiate. Then you inside differentiate, you give it the expression, then the variable with which you want to differentiate with, like that. Is that clear?
Yes, it is.
Again, you can say differentiate expression, then now it's time to differentiate with respect to y. Okay, there. It should be possible after you differentiate that you can store your whatever it is you've differentiated. For example, when we do this differentiate of the expression with respect to y, when we differentiate with respect to y, this is what we get. But we can store these. We know this is the first derivative. We can store these. The derivative, we can store that. Then there it is. Then after you store your derivative, you can also differentiate it again, so that you can get your second derivative. But this time around, maybe you would want to differentiate with respect to x after you differentiated with respect to y. So you could say derivative with respect to x this time. If you do that, then you get your 2x. Okay? So that you're not limited to what you can do. What you can do is basically up to you. It's whatever kind of differentiation you use. Time if you're differentiating with respect to x, you're differentiating with respect to y, then you can also store your derivative. Then after you store your derivative, you can use that derivative you've stored to differentiate it again, so that you get whatever it is you want. Is that clear?
Very clear.
Yeah, like the way we normally do our mathematics. There's another expression here, sine. The sine of x squared, which is what you have there. You can differentiate it this way, like that. That's okay. You can also, as you have seen, you can do a differentiation of the expression with respect to x, like this way. You still get the same. So that's up to you. I think these are the examples. Basically, I just trying to show the same stuff. I think what was more important for me is to show how you could carry out the differentiation two different ways. So that's how you do your differentiation, depending on what kind of differentiation you want to do. The last, but one of the last things also, you probably want to do integration. Now, in the case of integration, let's create something which is very simple, an expression which is very simple. For example, x. Then, so this is our expression x. That's our x. So one way you could integrate like this: expression dot integrate. Then the variable of integration, you want to integrate with respect to x. If you do that, this is what you get. You get x squared divided by 2 as your integral. You could also, this is an indefinite integral. You could also decide to do a definite integral where you've got limits of integration. So in that case, you could go like, before I go to that, let's also, oh, okay, fine, yeah. You could also decide to do a definite integral where with limits of integration, for example, like this expression dot integrate. Then here, inside here, so here we just at x, where we're x as the limit of, as the variable of integration. But if you decide to do a definite integral, then you have a tuple inside. Inside this tuple, you put your x, which is the variable of integration, then the two limits of integration, starting with the lower limit followed by the upper limit. So in this case, if you did that, you're integrating with respect to x, then your lower limit is 0, your upper limit is 1. When you do that, this is what you're going to end up with. You're going to end up with an integral which is equal to half. That's what makes sense. If you put 0 here, you get 0 divided by 2. If you put 1 on x, you get 1 squared divided by 2. That's the half. Is that clear? Is it clear?
Yes, clear, sir. But now, what if you are integrating a constant? How do you explain it?
If you're integrating a constant, okay, so that constant could be a number, right? So in that case, you create an expression. Let's say expression. Let's say our constant is what? It's 2. That's fine. Then you what? That's 2. Then you go about your integration expression dot integrate you integrate the expression with respect to x. I hope it works. So this should give you int object has got no attribute. Let me see. Integer. Enter. Population. Integer. Enter. Let me see. No. See, from just a minute, from Senpai, import integer. Let's hope it works. Then two. Okay. Yeah, there. You've seen? So first you have to import this guy. You have to import this thing called integer, a function called integer, which is going to create a number. You give it some number, then it's going to create a number which symbolic Python is going to understand as a constant or whatever it is supposed to be. For example, it could be not a number. I think we could have it as maybe a. I think it should be able to. Is it going to work? No, it won't. No, you just need a number. For example, 2 like that. Then that, then you do that. You could create something. So this is for a number, but you could also have constants which are not numbers. So in that case, if you've got a constant which is not a number, you have to create it as a symbolic. What is as a symbolic variable. But in this case, this is about a number. If you have a number, then you have to integrate it like that. Then you do that. If you, for example, I could say you create a symbolic constant k or a variable k, then I say symbol k, okay. Then I could say expression or a constant, whatever it is. I could say constant. Okay. Then I could say differentiate constant with respect to x. If I differentiate constant with respect to x, then I get a 0. Oh, what was it? Integrate, not differentiate. Integrate. Integrate. No, this one won't work. So this will have to be constant dot integrate I get that. I get kx. See that? So basically,
Very clear.
yeah, okay, that's good. So basically, that's how you do your integration. Like the way we did with differentiate, you could also do the same thing. We could just say if you don't want to go along this way of integrating where you have got some expression or a constant, then integrate. You could also just import integrate yourself. Say from Sympy, import integrate. So from Sympy, import integrate. If you run that like that, then now you would put your stuff in here. You check, first of all, let's check what our expression is. Our expression is 2, if that's what you want. Okay, let's change it to x. Okay, then we display the expression. Okay, then you could do this, integrate. Then you put expression, then the variable of integration. When you do that, you would get your x squared divided by 2. You could also, in this case, do integrate expression. Then if you want to include limits of integration and the variable of integration, those limits of integration, the variable of integration, you have to put them in a tuple. So that's going to be the expression here, which is x. Then the variable of integration will be the x. The limit of integration, the lower limit to be 0, the upper limit to be 1. So you'd have to enclose this thing in a tuple like that. Then you do that, that's what you get. Okay, if your expression in this case is we say an integer, what? It's a number 2, then just a number, then you want to integrate these 2. So you'd say expression integrate with respect to x. So that's going to give you this 2x, because it's just a number. You're integrating with respect to x, so you're going to get 2x. You can include limits of integration, the same, from 0 to 1. Sorry, here. Integrates expression like that. You get your 2x. Then here, expression, limits of integrations like that. you'd get your 2. Yeah. You could also do the same with a constant. Remember we created constant? Constant?
Yeah.
Yeah, so integrate constant with respect to the whatever constant is. Remember our constant is k. Our constant, that is k, so integrate constant with respect to x. That will give you kx. Then you could also do same constant with, you could do that with some limits of integration, 0 to 1, or you could put 2 like that. If you did that, then you end up with 2k. So that's how you do your integration. You choose which way you want to go. Either you want to use the dot, the one with the dot notation, or you want to use this one with the functional way. Either way is fine. Any question?
No question.
Okay. Lastly, you could also actually get some expansions. For example, Maclaurin series expansion, the Taylor series or the Maclaurin series for some simple functions. For example, if you want the expansion of cosine, cos x, so you'd say cos x, then you put a dot, then series. Or I think it's possible you can do that. You get your series expansion for the cosine function. Or you could go this way from Sympy, import series, that. Then after importing series, you should be able to do series cos x. It should give you that. Same. Is that clear? Does that look familiar? Your Maclaurin series for cos, for the cosine function?
Yes, it does.
Yeah, you could also to obtain a series for the sine function, sine x series, like that. Or you could just go by doing series sine x. You'd get that. Probably a more interesting series, not a ton, but a more interesting series would be an exponential one. The series exponential series, e to the power x. The series for that is this one. You could also get the same by doing series exponent of x, which is that. You could do it with negative x, exponent of negative x. You would get that. So there'll be, where there is odd terms, there'll be negative showing up. You could do a series exponent of negative x, like that. So that's how you do your expansions. This is typical mathematics, and this is some of the mathematics which can be done with symbolic Python. So in the case of your series expansion, this is typically second year mathematics. Some integrations, first year and second year mathematics, integrations and differentiations. So it could come in very handy when you know exactly what you want to do, and you're just interested in what the answer is. Or maybe if you've got assignments, mathematics assignments, then you want to see what the answer looks like. And when you work out your assignment, because as you can see, it doesn't give you how it's working it out, but it gives you what the answer is supposed to be, so that you can compare your answer with whatever the answer you found with what the answer is supposed to be. Is that clear?
Yes, it is now for the question, sir.
Yes.
For the same symbolic Python, so to say,
Mm.
is it compatible with the getting the range like we used to do for numbers, and you give it a range, or maybe this one is not applicable to such things?
No, no, no. This is like just you doing your mathematics on your own with pen and paper.
Okay.
Yeah, that's what it does. That's what it tries to do.
This one can't be like used for math plot lab.
It has such
The
capabilities.
example.
It has such capabilities.
Oh,
Yeah, we'll try to look at. There is so much. Basically, I think there's so much. I think because next week I want us to start actually doing computational physics. So, and I wanted to introduce this because this gives us a quick way of finding out if we have the answer, right? What the answer is, because it can solve certain things. So we want to have two ways of doing things. One, we want to do things numerically. Then two, we want to do things analytically. So that we can have two ways of comparing. Oh, so you can do this way, you can do this way, and we see what our answers look like. That's why, in a large way, that's why I wanted to introduce this. So that you're familiar with what symbolic Python can do, so that even as we start doing our course, as we are doing numerical computations, we can also, you can solve something numerically, but you can also solve something analytically, so that we see what the answer is supposed to look like. Are we clear?
but yes, like I'm clear. I just want to find out, 'cause on my notebooks, this one I don't have. So I don't know if you just uploaded it recently, or maybe it's not on the.
It's not yet there.
On the
This is not yet there. This I just prepared over the holiday here. Over this holiday.
That's how I'm like.
Yeah, this is not this. I think the only one which is there should be even there should be a video on symbolic Python notebook. I don't think I've uploaded it yet. Okay.
Okay.
Yeah.
It's interesting. I would like to have it. I'm kind of interested.
Okay. Fine. We're going to put all these things there. All right.
All right, then.
Okay, I think let's come to an end here. 16 hours, we've spent our hour. Tomorrow we are not going to meet, like I said, because we want to line up for the COVID vaccines also, so that we can try to get some protection, because people have to move around and stuff like that. So it will be it will be useful. So tomorrow we'll not have class. We're going to meet next week. When we meet next week, we're going to start looking at numeric Python. So we're going to look at our first topic of of computational physics. So we start with our first topic and see how we do things numerically. Then what tools Python provides for solving such questions numerically, and also how we can solve the same things using symbolic Python and stuff like that. Okay. So, see you next week.
All right.
Right, cheers.
Thank you.
You're welcome.